Hello Primary 6. This video is revision on lesson 2 Law of Levers. In this lesson you should be able to state the law of levers and apply it to solve problems. You also should be able to distinguish between the three classes of levers according to their conservation of effort, meaning what classes of levers save effort and what classes do not. You also should determine some benefits of the third class levers. First, let's review the structure of the lever, or what are the main parts of the lever. The lever consists of three main parts: the fulcrum, effort force, and resistance force. The fulcrum is the fixed point on which the rigid bar or the main body of the lever is supported on or rotates around. The effort force is the force done by the person or the hands in order to equilibrate or overcome the other force, which is the resistance. So the resistance represents the load or the weight of the object that we want to overcome. Look at the picture. The man is trying to lift up the box, so he needs to exert effort. How much effort does he need to lift up the box? By using the law of levers, we can find out the effort force needed to overcome a resistance, and also we can decide if this lever saves effort or not. So, the law of levers allows us to calculate how much force is needed to overcome a known resistance. But we have to know the value of the arms of the lever. What are the arms of the lever? Since we have two forces, effort force and resistance force, so we have two arms: effort force arm and resistance arm. What is the effort force arm? It's the distance from the fulcrum point to the effort force, while the resistance arm is the distance from the fulcrum point to the resistance. The length of the arms is very important to determine if the lever saves effort or not. Let's talk about the measuring units. The unit of measuring the effort force and resistance forces are the Newton, the same as the unit of the weight. While the unit of measuring the arms, either the effort force arm or the resistance arm, is the meter or centimeter, because they are lengths being measured. So what is the law of levers? The law of levers states that the effort force multiplied times its arm is equal to the resistance multiplied times its arms. What does that mean? It means that if we multiply the effort force done by the person times the effort force arm, which is the distance from the fulcrum to that effort force, their multiplication product would be equal to the resistance force if multiplied times the resistance arm. We are going to talk about each class of levers and whether it saves effort or not. Let's start by the first class levers. Do you remember what are the first class levers? They are the levers that have the fulcrum in the middle between the effort force and the resistance force. We need to know if the first class levers saves effort or not. Again, that depends on the length of the arms. In the first class levers, there are three cases according to the length of the arms. In the first case, the fulcrum was exactly in the middle between the effort force and the resistance force. That means that the two arms are equal. The effort force arm is equal to the resistance arms. And according to the law of levers, if the two arms are equal, so the effort force would be equal to the resistance force. Does this lever saves effort? When can we say that the lever saves effort? In order to say that a lever saves effort, the F, or the effort force, has to be smaller than the resistance, which means I have to do an effort which is smaller than the resistance to save my effort. Since the effort force is equal to the resistance force in this case, so this lever does not save effort. Now let's see case number 2. It's a first class lever with the fulcrum between the effort force and the resistance. Here, the fulcrum is far away from the effort force. So the effort force arm is longer than the resistance arm. Since the effort force arm is longer, its force, F, is the opposite. It would be smaller than the arm. Again, if the effort force arm is longer than the resistance arm, the force of that arm, which is the effort force, would be smaller than the resistance. Does this lever save effort? Yes, we have just said that if the F, the effort force, was smaller than the resistance, this lever would save effort because we are exerting less effort than the resistance. Let's see case number 3. In that case, the fulcrum was closer to the effort force. So the effort force arm was shorter than the resistance arm. If the effort force arm is smaller or shorter than the resistance arm, the force of that arm, which is the F, would be the opposite, would be greater than or bigger than the resistance force. Does this lever save effort? In this case, I'm doing effort, which is F, bigger than the resistance. So of course this lever does not save effort. Why? I'm doing extra force, very large force, because the effort force arm was shorter than the resistance arm. Now let me ask you, do all the first class levers save effort? No, not all of them. Some of them. The first class levers sometimes save effort, only when the effort force arm is longer than the resistance arm. Because when the effort force arm is longer, the F, or the effort force, would be smaller, and that's what we need. We need to do less effort in order to save our effort. So this type of lever, case number 2, is the one that conserves or saves effort. Let's take an example. Read this problem. The length of the force arm of a first class lever is 5 centimeters, and the length of the resistance arm is 15 centimeters. If the resistance has a value of 300 Newton, calculate the value of the affecting force or the effort force. Here, since it's a first class lever, we have the fulcrum in the middle between the resistance and the effort force or the man. Here, before we answer the problem, we have to write down the law. The law of lever states that the effort force times the effort force arm equals to the resistance times the resistance arm. Here we have the force arm given, 5 centimeters. Here is the force arm, the distance from the fulcrum to the effort force, which is 5 centimeters. And we also have the resistance arm given, which is 15 centimeters. Where is the resistance arm? It's the distance from the fulcrum to the resistance, the heavy load, which is 15 centimeters. So here we have the two arms given. We have the value of the load or the resistance, which is 300 Newton, and we need to find out how much force is needed to equilibrate or to reach a balance or to lift up that load. By substitution, we found that here the effort force is unknown. The effort force arm was 5 centimeters. The resistance it's given, it's 300 Newton, and the resistance arm is 15 centimeters. To calculate the effort force, we multiply 300 times 15 over 5. So the final answer would be effort force equal 900. And since it's a force, the unit would be Newton. Now let me ask you, does this lever save effort or not? We have to compare the effort force F with the resistance R. Here, the resistance, the heavy object, was 300 Newton. In order to lift it up, we needed to exert force of 900 Newton. Here, we exerted an effort which is much bigger than the resistance force. Did we save effort? No, this class or this type of levers does not save effort because the F or the effort force was greater than the resistance. The effort force was 900 while the resistance was only 300. Why the effort force was much greater than the resistance? Look at the arms. Here the effort force arm, the distance from the fulcrum to the effort force, was shorter. Since the arm is shorter, so the force would be bigger. So this lever does not save effort. Let's see another example. The exerted effort of a first-class lever was 10 Newton. And the length of its arm, which is the effort force arm, is 30 centimeters. And it's affected by resistance of 60 Newton. Find the length of the resistance arm. First of all, we have to write down the law. The law of levers states that the effort force times the effort force arm equals to the resistance times the resistance arm. Do we have the exerted force? The exerted force is the force done. It's the effort force. Yes, it's 10 Newton. Do we have the effort force arm? Yes, it's given. The length of the effort force arm is 30. Do we have the resistance? Yes, the resistance was 60 Newton. Here, the unknown, or we want to find out the length of the resistance arm. So again, by substitution, here the effort force was 10 Newton, the effort force arm was 30 centimeter, the resistance it's given, it's 60 Newton, and we don't know the value of the resistance arm. The resistance arm will be equal to 10 times 30 over 60. So the final answer would be resistance arm equals 5 centimeter. Now let me ask you, this first class lever saves effort or not? We have to compare the F and the R. The effort force done to overcome the resistance. Here, in order to lift up a resistance of 60 Newton, we exerted force of only 10 Newton. Of course, this lever will save the effort because the effort force was smaller than the resistance force. And why was the effort force smaller? Because of the arms. Look at the effort force arm. It was 30 centimeters, while the resistance arm that we have just calculated, it's only 5 centimeters. Again, if the effort force arm was longer than the resistance arm, the effort force will be smaller than the resistance, and that's what we need. We need to exert less effort than the resistance to say that this type of levers saves effort. One more example. In a lever, the length of the force arm is 100 centimeters and the length of the resistance arm is 15 centimeters. Calculate the value of the effort force if the resistance equals to 400 Newton. And what is the type of this lever? From the figure, we notice that the resistance was lying in the middle between the fulcrum and the effort force. And we studied that in lesson 1, the second class levers have the resistance existing in the middle between the fulcrum and the effort force. So what type of lever is it? It's a second class lever. Here we have the two arms given. we have the effort force arm 100 centimeter, which is the distance from the fulcrum to the effort force. And we also have the resistance arm given, which is the distance from the fulcrum to the resistance. The resistance was 400 Newton. So we need to find here or to calculate the value of the effort force. In the beginning, we have to write down the law of levers. The law of levers states that the effort force times the effort force arm equals to the resistance times the resistance arm. Now we have to substitute each value. Here we don't know the effort force. This is what we need to calculate. The effort force arm was 100 centimeter. The resistance was 400 Newton and the resistance arm was 15 centimeter. So to find out the effort force, we multiply 400 times 15 divided by 100. The final answer would be effort force equals to 60, and since it's a force, the measuring unit is Newton. Can you say if that type of lever saves effort or not? We have just said that this is a second class lever. Does it save effort or not? Compare the effort force with the resistance force. The effort force that we calculated is 60 Newton, while the resistance force was 400 Newton. So, in order to lift up a load or an object which was 400 Newton, we only exerted force of 60 Newton. Here, this lever saves effort or not? Yes, it does, because we said that if the effort force was smaller than the resistance force and I did less effort than the R, this effort will save effort. And why was the effort force smaller than the resistance? Because the arm was longer. Look at the effort force arm. It's 100 centimeter, while the resistance arm was only 15 centimeter. Again, if the force arm was longer than the resistance arm, the force of that arm, which is the effort force, will be the opposite, will be smaller than the resistance, and that lever will save effort. So this lever, which is a second class lever, it saves effort. We now notice that some types of levers conserve effort while others do not save effort. When does a lever save effort? The lever saves effort if the effort force arm was greater than the resistance arm. For example, the crowbar. To know if the crowbar saves effort or not, we have to look at its arms. Where is the effort force arm? The effort force arm is the distance from the fulcrum to the effort force, or the hands. Here is the effort force arm. And where is the resistance arm? The resistance arm is the distance from the fulcrum to the resistance, or the heavy object. Here is the resistance arm. Are they equal? No. Here, the effort force arm is longer than the resistance arm. And we said that if the effort force arm is longer than the resistance arm, the effort force F will be smaller than the resistance force R. So the crowbar or this type of levers, it saves effort. So the first class levers saves effort if only the effort force arm was longer than the resistance arm. Let's look at the second class levers. The second class levers always conserve effort. Why? Because in the second class levers, the effort force arm is always longer than the resistance arm. Let's take an example. In this wheelbarrow, where is the effort force arm? It's the distance from the fulcrum to the effort force. Here is the effort force arm. And where is the resistance arm? It's the distance from the resistance or this heavy object to the fulcrum. Here is the resistance arm. Of course, as you can see, the effort force arm is longer than the resistance arm. So the F or the effort force will be smaller than the resistance, and that's what we need. So this lever will save effort. I want you to know that in the second class levers, the effort force arm will always be longer than the resistance arm. You know why? Because in the second class lever, the resistance will always be at the middle. So the effort force will be farther from the fulcrum. That's why the effort force arm will always be larger or longer than the resistance arm in the second class levers. So the second class levers will always conserve effort. What about the third class levers? No, the third class levers never save effort. They always do not save effort. Why? Because in that case, the effort force arm is always shorter than the resistance arm. Let's take an example, the fishing tool. Here is the fulcrum, here is the position of the effort force, and here is the resistance. Can you determine where is the effort force arm? It's the distance between the fulcrum and the effort force. And where is the resistance arm? It's the distance from the fulcrum to the resistance. Can you notice here that the effort force arm is shorter than the resistance arm? And we have just said that if the effort force arm was shorter than the resistance arm, the effort force will be the opposite. It will be bigger than the resistance force. So if the F is bigger than the R, that means we are doing extra force, a force much bigger than the resistance. So we are not saving effort. So the third class lever will never save effort. Now, can you answer this question? Does the seesaw conserve effort? Let's have a look. To determine if a lever saves effort or not, you have to see the length of the arms. In the seesaw, the fulcrum is exactly in the middle between the effort force and the resistance. And according to the law of levers, if the arms are equal, so the forces are equal too. Here, the effort force arm is equal to the resistance arm. So the effort force F will be equal to the resistance force R. If the two forces are equal, will the lever save effort? No, we said that the F must be smaller than the resistance, so the lever would save effort. So here the seesaw does not save effort because the effort force arm is equal to the resistance arm. The question is, if the third class levers never save effort, they do not have mechanical benefits, why do we use them? We use them because they have other benefits, such as we use them to increase the distance, as in the manual broom, or we might use them to increase the speed, like in the hockey bat. Or we use the third class levers to perform that task accurately, like in case of tweezers. Or the third class levers may be used to avoid dangers, as in the coal holder and the ice holder.